Does Jeff require an introduction?
Thank you. All right. Let's see if we can get the projector working. Awesome. Okay. Thank you to all the organizers for the workshop, organizing the workshop. I think it's going to be a really great day. I'm going to talk to you about some of the things that Mimi raised in her intro. You know, how can machine learning be used to inform and improve computer systems? And I'm going to present a bunch of different pieces of work. You know, some are like very specific, and I'll go into some details. Some are sort of more aspirational, and ways in which I think we as a community should be thinking about applying machine learning to systems. And this is presenting the work of many, many people at Google. It's not all my work, so just to be clear. But the key question for this community is how can we apply machine learning in more kinds of systems to make them better in various ways and also to make them more efficient? I think one of the things about Rich Sutton's article that I really like is the focus on search and learning is often something that makes, overcomes other methods and finds that the best way to solve certain kinds of problems, particularly in computer systems, I believe, is with lots of search and lots of learning. And I think we are starting to dip our toe in that as a community, but we're not doing it as much as we should. So traditional systems, I think, like operating systems, compilers, memory allocators, and so on, they don't make extensive use of machine learning today, but that should change and is starting to change. And I'll show you some examples of that. I was delighted to give a talk at the 2018 version of this workshop. And I said, hey, look at all these amazing opportunities in all these different kinds of computer systems, and how could they be, how could we use learning in various places? And then I said, here are some key challenges. How do we integrate machine learning into the guts of traditional systems? Because we're probably not going to rewrite all the world's operating systems and compilers. We need to make something that actually enables us to put learned decisions in the right places in those existing systems. How do we make machine learning work well in challenging environments? Rapid decisions can be needed. Like if you're trying to make a decision about a file system block cache insertion, that's a pretty tricky and challenging time scale at which you need to do this, or network packet arrival would be even more challenging. OS process scheduling is kind of in the middle. And then, all the usual concerns of applying machine learning to anything you also have in computer systems. How do you interpret the decisions? How do you understand them? How do you make them safe and reliable and robust and operate maybe within a range of things, but learn within that range, but not go too crazy? But here's the good news. Since 2018, there's been considerable progress on a lot of these techniques. So I will just kind of show you some of that progress and still point you in the way of places where I think we should be doing more. So one area is learned compiler choices, not heuristic-driven choices. And, for example, in a compiler and auto-tuner system, there's actually a lot of opportunity because it's a very measurable end result of what it is you want. If you have a harness, you can sort of measure the performance of code compiled one way or compiled another way with this flag or with that flag, and you can actually get a very clear reward signal of, how well is your choice doing. And so actually Mang Po is one of the primary author of this work, which is a flexible approach to auto-tuning multi-pass machine learning compilers. The basic idea is you have an evaluator with a learned cost model that can evaluate how quickly some piece of code compiled in a certain way would run. And in some cases, you can even do that without actually running the code. And then you have a code optimizer, and then you have a learned policy for how to set various compiler settings or choices within the mapping of high-level code down to the lower-level code and get a good signal of performance. So one example is operator fusion in a compiler. There's all these different shapes of arrays, and sometimes it makes sense to fuse them. Sometimes it doesn't make sense to fuse them into a single operation as opposed to something where you do one operation, put the results back in memory, and then another time, then go fetch the results again. And that depends on a lot of factors. The memory bandwidth on the device, the shapes of the arrays, all these kinds of things. And so you really like something that is actually learned based on the characteristics of the hardware you're running on. Layout assignment is another example. how should you decide to lay out the dimensions of a abstract tensor into actual, linearizable memory locations is another great example. And you get quite good speed ups. Taken together, all these different kinds of things can give you 5 to 25% speed up on a bunch of production models within Google's machine learning workloads by automatic tuning of the fusion layout and other kinds of things, which is quite nice. 5 to 25% is like free TPUs for everyone. Another area where we've seen some impact and some pretty promising results is in various kinds of allocation policies. So learned object lifetime prediction improves allocation policies. So here you have a typical C++ memory allocator like malloc or tcmalloc. And you're going to allocate some code, and then you get some object, a string here, and then you're going to delete it at some point. And the lifetime of that object affects dramatically what you should do. If it's a very short-lived object, it might make sense to put it in some thread local cache. If it's a very large, long-lived object, then you might want to put it in, more central memory, where you coordinate the largest blocks of memory with a coarser grain and heavier weight protocol. So you have a bunch of factors: the lifetime, the object size, and you have pages of memory. And whenever you put objects in any of one of these larger pages, that page is then going to stay alive in operating system data structures in ways that it won't if you free up all the objects in the page. So it's pretty important for you to be able to cluster objects with similar lifetimes so that they stay on the same page and you don't end up wasting memory. So in the bottom example, we have 2 pages here, 2 megabytes in size. The top one is nice because it's almost entirely full of live objects, but the bottom one is wasting a bunch of memory and has only a few objects live in it, but not 0, so we can't free the page. And one of the things that dramatically affects the lifetime of an object is in what context was it allocated? What is the stack trace of that's on the top of the stack when you are actually allocating the memory? And if you go up a few levels, you can often do a really good job of predicting from that sort of stack context how long the lifetime will be. And so if you treat call stacks as a natural language and then you can train an LSTM network on them, then you can actually get pretty good object lifetime predictions. The caching mechanism, basically you're going to try to predict short, medium, or long for your lifetimes. And you have an allocation, you hash the stack, that gives you a cache of the learned decisions. If you miss in the cache, then you do a more complex LSTM evaluation of the stack to try to give you a prediction. And this is a work by Martin Moss and others on how do you combine ML and lifetime predictions. And then you periodically discard the cache, because sometimes programs go through phases in order to sort of make sure that you're sort of adapting to the current behavior of the program. And that gives you a prediction. And so, for example, it's trying to predict, will this object live less than 10 milliseconds, less than 100 milliseconds, or less than a second? And you can then try to group these objects into the same pages. And if you fail to predict this correctly, then you promote that page to the longer-lived lifetime, and you also mark your earlier prediction as incorrect, like you should have said this is a medium length lifetime, not short. And then that helps you adapt to the actual behavior of the program. And this gives you actually a pretty significant improvements in fragmentation of memory. So if you look at the prediction accuracy is quite good for lifetime prediction. And because of that high prediction accuracy, it enables you to get a substantial reduction in the memory state, live memory state, compared to the base tcmalloc. So Llama is considerably improved there. And the live objects, that's the amount of live data in the programs. But you get a 19 to 78% reduction in fragmentation, which is quite nice. You can also use this for other kinds of machine learning accelerator memory allocation. And one of the settings here is that you actually often have repeatable workloads, say for an inference or a training pass of a machine learning model. The allocations are actually quite predictable when you will allocate a bunch of memory for a big tensor, when you will free it. And so that is a slightly different setting now where you have memory allocation. You want to determine how to place buffers within machine learning accelerator memories. But in this setting, you actually know the starting and ending lifetimes of the memory. So you know when it's going to be freed when you allocate it. And that enables you to do a much better job of making a more global decision about where to allocate memory. And actually what you're trying to do is allocate a particular address to this particular allocation. So we know the lifetime of the object, we know when it starts and ends in time, and we know the size. And so given a sequence of fixed size buffers with known start and end times, can we place them in memory so that we don't never exceed our memory? And it's super hard and complicated. And heuristics are super fast, but they don't always find a good solution. And the other alternative is solvers, which are super slow, but find a good solution. And so telemalloc is some really nice work where you try to achieve the best of both worlds by combining heuristics and solvers. And the way this works, here's an example of the limitations of heuristics. If you make a decision to allocate that blue object there, then at some point you end up with a heuristic where now you actually don't have any space for this object to actually go because of that decision. Whereas if you decided to put it here, you would be fine. So with Telemon, you have a search heuristic, you have a constraint satisfaction solver, you have a decision and success or failure, and you can backtrack. And you have some constraints, like amount of memory and so on. The issue with the backtracking problem is you don't know how far to backtrack. And so that's where using machine learning actually helps you, is where should I backtrack to? And you can use machine learning to learn a better backtracking policy in the constraint solver. And so by imitation learning, you can try a bunch of constraint solving and find by evaluating what the best backtrack point is for a particular scenario, then you can actually give a model that is trained to give you learned backtracking policies, so that for a particular, for the settings in which you're allocating memory, the system will learn to backtrack in the best way and actually be able to do constraint satisfaction much more quickly. And because you're then still using a solver, you don't have correctness issues. It just helps the solver run more quickly. So you can enforce correctness by guiding the solver and instead of predicting decisions directly. And that ships in production, starting in Pixel 6 and TPU v4. So you're probably maybe using this if you have a Pixel phone. The other thing I mentioned about systems is that often you want to be able to integrate really lightweight learned decisions into the middle of some complex already existing systems code, like a compiler or an operating system. So SmartChoices is a system that we've been working on at Google to make it easy to integrate these sorts of learned choices into such code. And has a relatively narrow API. You can create a choice of some context, and then the ARM type is the sort of set of decisions you're trying to make a choice over. The context type is the set of information you want to use in order to help learn that decision. And then you make a choice, and later you can get some feedback about how good that choice was. And then the system will take that feedback and use that to hopefully improve the decisions over time. Oh, and then you give feedback with this call on the handle you got when you made a choice. So there's a couple implementations. One is choose can actually be quite fast because it uses a variety of different machine learning models, and there's a very fast bandit-based implementation that can make choices in like tens of microseconds. that runs in process. Sometimes this give feedback can happen really quickly in the same process. Like you get very clear signals of like, was that actually a good choice or a bad choice, or what was the cost of that choice? For other uses, then give feedback happens much later and sometimes in completely different parts of your distributed system. Like maybe you sent something back to a user clicked on something, and that gives you a feedback signal, but it shows up on web server 97 instead of web server 4. And then in that case, we have a more complex distributed system that actually takes the choices and the actual feedback, joins them all together in an offline processing step, and then can retrain the model based on that feedback, and then can push new models out to the serving system of all the different software that's making use of that. So here's, we've been using this for a bunch of different use cases within Google, and a growing set, because this API is actually pretty nice and simple. Like wherever you have an if with a heuristic, it's not too hard sometimes to transform it into something that uses this kind of learning. And so here's a system where we decided to learn the right video to evict from the YouTube cache at a different satellite data center. So we have these caching locations all over the world where we try to have the most popular and watched videos present locally, so we don't have to go to a farther away data center and stream the data across a more expensive network link. And this system was able to actually reduce the cache miss rate, or measured at the byte level, by 9.1% with a relatively modest CPU cost, which is quite an impressive an important statistic for us. It's also been used to, for example, optimize thread counts. If you have a complex flight request, you need to know how many threads to use in order to service that with a reasonable latency and reasonable throughput. And if you use too many, then they don't share information enough, and you end up doing a lot more work than you needed. But if you use too few, then the request can take a long time. And you want to be able to learn based on the sort of parameters of the search how many threads you should use. Work partitioning is another thing. Refresh rates in an advertising system. How often should the client go and fetch new information about what ads are available and so on. User interface optimization can actually be done this way. So you have what buttons should you show to this user based on their past behavior. You can actually customize the UI and have a learned kind of choice based on user attributes. Okay, faster inference, I think, is an important area for all kinds of machine learning use in the world. And making these inference costs and latencies really low really greatly broadens the impact that these models can have in the world. And so bringing better quality models with more capabilities to more users more quickly. And we care about high quality, fast models. Our Gemini 2.0 launched this week. One of the things that people seem to really like about it is the latency is quite low. So here's a tweet from a user who switched from 1.5 flash to 2.0 flash, and you can see when they switched, and the latency on whatever system they were building actually got a lot better. There's a whole bunch of inference cost reduction techniques. So one thing you want to do when building an inference system is you want to consider the expected inference load when you're deciding on some model attributes. So there's been a lot of attention to the sort of optimal choices for scaling large models with this paper, Training Compute Optimal Large Language Models, also known as the chinchilla scaling laws. So it's really good, but this model doesn't consider the inference, how many times you're going to use that model for inference. And really what you care about is probably some estimate of the total training cost plus how much inference is going to cost you over how many requests you think that model is going to have to serve. And if you don't consider the inference cost, then the chinchilla scaling laws are great. But if you do consider the inference cost, then it leads you to pretty different decisions in a lot of cases than just the one that's optimal for training compute. And so a couple of different techniques that we've found pretty effective for reducing inference cost. One is you want to produce higher quality, smaller models via overtraining. So so you can have a choice. If you have a certain amount of training compute, you could choose the chinchilla optimal model size for the amount of training data you have. Or you could shrink the model size in order to make more passes over that data in the same amount of training compute. And if you shrink the model size, that makes it cheaper for inference. And there's kind of a sweet spot of, between 1 and 5 epochs over your training data generally doesn't affect the quality that much, but it can have a pretty dramatic effect on the inference cost of the model because you can make your model, 3-5 times smaller. Another approach, another complementary approach is to use distillation to take very large models and then transfer the knowledge in those large models into a much smaller model, and that tends to be quite effective in order to get smaller, much more capable models. And that's kind of the original distillation paper. Another aspect is how do you create models that have a lot of capacity but maybe are not fully activated on every example. You want to have parts of the model that are learned to be activated based on different kinds of contexts or that particular token or setting or prompt. And we've been doing work in sparse models for quite a while at Google. And Gemini 1.5 Pro, for example, uses a mixture of experts architecture, building on this long line of research about how to decide which portions of the model to activate. And this gives you a very large footprint model, which is a little annoying for inference because you have a very large set of accelerators you need to put your model on, but any given token or request may touch just a handful of the parameters of the model. Another important sort of machine learning applied to computer systems. So I think of inference time compute and low latency inference as a computer systems problem. And there are actually nice machine learning solutions to making your inference problem better. So speculative decoding is an example where you enable faster decoding from autoregressive models, usually 2 to 3x improvement in performance. And you change only the decoding algorithm, so you don't need to make any architectural changes, you don't need to do any retraining. And there's no trade-off. That's basically guaranteed identical output distribution. So this is where you find the details, fast inference from transformers via speculative decoding, Leviathan and all. And so the observation that spurred this is decoding from large transformers is memory bound because you actually do relatively little compute relative to the amount of parameters you bring in from memory. So the hardware can do an awful lot of floating point operations per byte read. But if you do just decode one token, you're not making use of that hardware's potential floating point operations. And some tokens are easier to predict than others. Can you tell me what the square root of 7 is? Sure, the square root of 7 is, those tokens are easy to predict. Then 2.646 is a little bit harder. And so the idea is you have a drafter model that's much, much smaller than your main model and quickly generates several tokens of like, what should the next 4 tokens be? And then the large model can check these in parallel. So now, instead of just decoding one, you're fetching the parameters of the large model from memory in order to check this window of 4 or 8 tokens and to see how many of them agree with the larger model's choices. And if say the first 3 out of 4 agree with the large model's choices, then you're going to just advance and emit those 3 tokens and then go on to decoding from that position. So you now have only fetched the parameters from memory once for the large model instead of 3 times in order to decode 3 tokens. And there's a nice little animation of how this works. If you have a large slow model that's just doing one at a time, that's what's happening. But if you have a drafter model that is much smaller, it predicts these yellow windows. I'll restart the animation. Oh, sorry. Okay, it's going to restart. So the yellow windows are what the drafter model is predicting, and then some amount of that prefix is verified by the larger model, and then we just advance. And meanwhile, our large slow model is large and slow at the top. Okay, now we're going to get into an area where I think there's real opportunities for dramatically changing what we're doing in a sort of a major field that's important for all of computing. So first, there's an observation. Designing a new chip currently takes dozens to hundreds of person years and usually 18 months of effort. and lots of kinds of specialized expertise. And the cost for this on the leading edge processes is hundreds of millions of dollars. So what could we do as a field if designing a custom chip was much, much cheaper, much easier, much less effort? What if it took a few people a few weeks? That would be amazing. It's really, really hard to get there, but that's, I think, something that learning will help with. So there's a whole bunch of phases in chip design that are time consuming. There's the architectural exploration where you make sort of very high level decisions of, what kind of caching hierarchy are you gonna have, how big are the caches gonna be, how much memory bandwidth are you gonna have, what size are your computational units gonna be, how many of them will there be. And then there's, once you've made some decisions, a mapping of that to a lower level synthesized logic that you can actually then sort of start to lay out and place and route and also verify. And one of the problems with chip design is a lot of that RTL synthesis is done by hand today. So it's sort of done by lots and lots of hardware engineers and then hand verified by other verification engineers that it actually matches what we want the chip to do. So how can we get to the point where designing a custom chip takes a few people a few weeks? First, we need to change the computing paradigm for how chip design is done. A lot of commercial CAD tools are things that run on a single machine on CPUs. And if you're like a modern, super high-end x86 box will get you 100 billion instructions per second or so. And many of these commercial tools will then parallelize across threads or cores in that box, but will not go beyond the confines of a box for a single problem. We know parallelism is a really good solution for a lot of kinds of large-scale problems, and we know if you could use 1,000 machines to tackle a problem, often you can get really nice speed-ups. So instead of phases that might take 12 hours or so to run overnight, and then you kind of look at the output and you're like, oh, that was sad, I wish it was better, let me fiddle with it, and let me run it again overnight. Instead, you could have something that gives you feedback in a much more rapid manner. Maybe one of these phases could take minutes instead of hours. The other thing is we should make use of machine learning compute if we're going to learn things. So in general, I think we need to use much more compute and much more parallelism, both parallelism of CPUs across lots and lots of machines, and also parallelism across machine learning accelerators. So remember, I told you designing a chip takes hundreds of millions of dollars. So what if we were willing to spend $10 million on compute in 21 days? Because I said I want a few weeks. So if you use a Google Trillium TPU chip, that costs you $1.22 an hour. And if you really want to spend your $10 million in 21 days, that means you could have access to 16,000 of these chips for 21 days. And that's 15 exaflops. That's quite a lot of compute. And if you're willing to spend $100 million, you get 10 times that. So I think with this amount of compute, you could actually do a pretty good job of exploring a space in a more automated way than we're currently doing with chip design. So how will we make use of this? Okay, so one is we want to use end-to-end learning as much as possible. So right now, there's almost no learning at all in most of this, and certainly no end-to-end learning across the entire sequence of steps. And end-to-end is really important because a lot of choices you make up here really have dramatic effects on the placement and routing of the chip, on the size and the area, and you really want to have that taken into account in the way you're exploring the high-level choices. So learn to automatically do architectural exploration and synthesis. Maybe for a restricted class of applications would be a good way to start in this endeavor. Don't try to do any chip. Just say, hey, we care about a subset of domains. Let's look at how do we automate design of a chip for this subset. So one of the problems is in the approach, the translation of high-level architectural specs to low-level, I mentioned this, low-level RTL is done manually by many hardware engineers. If you use known to be correct transformations, Then you're more in a state like software development where you have a compiler, and you usually don't mistrust your compiler in taking your high-level language and mapping it into a low-level system. So if you do that, then you need much less verification in your chip design because you've basically automated synthesis. It's explored a whole bunch of choices. It's come up with some good choices, and those are sort of provably correct transformations into lower-level language. One of the reasons people don't use high-level synthesis today is that it doesn't take into account the ramifications on downstream choices. In particular, downstream placement and routing is not really considered when you're choosing, should I synthesize this way, A, or this way, B. And that really has dramatic effects because then it's not actually choosing on the objectives you really care about, which is ultimately what is the power area and the timing of the actual generated circuits. So this reminds me of one of the earliest papers I published in grad school, which is a compiler paper, where when you're making a decision to inline something in a compiler, you have this choice of should you inline it or not. And most compiler optimization heuristics are looking at the kind of high-level source code or a higher-level representation of that source code to make a decision about should they inline it. But what that doesn't take into account is all the potential optimizations that might occur if you inline this code in this context where the second argument is a 7 and we know the type of the third argument is a float. And so if you're actually able to take into account all those decisions, sometimes inlining decisions that seem like you definitely shouldn't inline are actually clear ones to inline because maybe the second argument being 7 enables the entire routine to collapse down to returning 15. And so what we did in this work was we actually would try inlining, and then we would measure the effect of what optimizations were enabled by the information we had available at the call site. And then we would use that information in the most general way possible. So we would say, oh, we were able to constant fold the second argument with this other operation. So any constant in the second argument will be a good idea, not just the value 7, so we could try to generalize. If you squint at it today, you could say that's kind of like learning and generalization, but it was really just a sort of hand-coded data structure that would have sets of types that we were trying to learn over. So I think we need to do something similar for the end-to-end architectural exploration. We want to be able to very quickly evaluate the downstream effects on placement and routing in high-level architectural exploration and synthesis. And honestly, we want all kinds of feedback loops that are varying, that are as fast to evaluate as possible, and probably the longer range ones here take longer to evaluate, so you use those less often, but you use the very fast to evaluate ones as proxies for what the downstream costs are, and you can learn those cheaper to evaluate ones that are hopefully at least correlated with the longer, more complex to evaluate ones. We also maybe want to enable the 3 humans who are helping supervise this chip design to make a relatively small number of really consequential decisions, really to guide the overall process. Yeah, even correlated but not perfect outputs are useful for doing RL. Yeah, and if we can get an estimate of the implications of some decision in seconds, that enables us to actually consider it in the loop of making synthesis decisions. So one area where we've done a fair bit of work already is in learning to quickly generate high-quality placement and routing decisions using reinforcement learning. So this was a paper we published in 2020, and then was published in Nature in 2021. We forgot to give it a name. Oops. It's now called AlphaChip. The high-level approach of how this works is you essentially take some block, so one part of a chip that you're trying to lay out all the components in that block. You cluster the components, so instead of millions or tens of millions of things to place, you have order hundreds of things to place, and you're placing clusters of things as well as macro things that represent things like various memories of various sizes. And the RL algorithm just makes a series of decisions about where should each of these hundreds of things go on the canvas, and then it can measure via a lightweight proxy cost, what effect does that have on total wire length in the block? What effect does it have on area? And it can also estimate some aspects of congestion. Like I've placed a bunch of things near each other, it's likely to be more congested in this part of the chip. And so what we see is that we're actually able to, in a much more rapid fashion, get high quality layouts. So this is the machine learning placer on the right there, and a human expert on the left, laying out different blocks where the white things are macros and the green things are logic. And so in a much more rapid fashion, you're able to get good answers. Perhaps more importantly, though, one of the things we do in this work is we pre-train the system on other blocks so that it has experience with chips. Like it's a really good idea if you're going to do reinforcement learning to give it as much experience in the problem you care about as possible. And so the blue line is what happens if you don't pre-train it on any other chip designs and you just start it off totally randomly and say, hey, okay, you figure it out. And what you see is it's actually able to get to a pretty good state after a long period of computation, but it takes a while to even figure out, this big drop after 20 hours, which is sort of just the idea that you should put the logic in the center and then the macros around the edge, which is what a normal, like a human chip designer would have that intuition right off the bat. But the green line is what happens if you pre-train. So if you pre-train, you actually get really good results, actually a bit better than if you just train for a long time on the block itself. But more importantly, in 1 second, it can give you a pretty decent estimate of what is the placement cost of this particular way of placing things. And so by having that feedback in 1 second instead of 12 hours, that should enable a lot more decision making at the higher level and iteration of choices at the high level with a good sense of what the implications are for that lower level choice. And this green line was pre-trained on 20 blocks before trying to place this particular block. Imagine if it was pre-trained on a lot more. It would have a even more good estimate right off the bat. So AlphaChip has now been used in multiple different TPU generations. The wire length improvement over human experts is improving quite dramatically, generation over generation. It's also been used for data center CPUs and other chips. It's also been open sourced, so people can use it for chip designs of their own. And we've released a pre-trained checkpoint as well for the 20 blocks that were used in the Nature paper, so people can get that green line performance right out of the box without having to do their own pre-training. Okay, learn synthesis. I think is important. We've been doing some work on that. We don't have a paper published, but we competed, some Google Deepmind folks competed in a contest and won the contest pretty handily on how do you automatically synthesize logic for particular, interesting problems. That seems like an important characteristic. And one thing that this enables you to do is not synthesize like an entire chip, but synthesize important subproblems. So if you need like a 5-bit adder or something, what's the most efficient logic for doing a 5-bit adder? This kind of approach is really good for that. And then you want to learn to do architectural exploration. And the kinds of choices you make here, there's a space of architectural choices, and you can imagine exploring that space with RL using both a high-level simulator, which gives you answers quickly, but also perhaps in this new end-to-end world, also making occasional use of more downstream reward signals that are closer to the actual answer you might want. And you get pretty significant improvements if you specialize in architecture for a particular model or a class of models rather than having a general purpose one. That's the green lines versus a sort of approximate version of a TPU v3 baseline in blue and a TPU v3 plus the compiler improvements that we're also simultaneously exploring in red. But you see specializing the architecture plus doing a good compiler for it gives you the best wins. Okay, so if you put it all together, I think we can learn to do all these different things end to end, be amazing. It's a super long, ambitious idea. Probably won't happen overnight, but it's an area where I think with the right feedback signals, we can do it. Okay, so if you could really make designing a chip 20x to 100x cheaper, there'd be all kinds of specialized uses you'd make of chips that are not economically reasonable to do now. Okay, so in conclusion, ML for systems, having dramatic effects across many areas of computer systems, learning and search, super important. Use those, they're your friend. And thank you very much. And I can put up. All right.
All right, we have time for maybe like 2 questions. Someone very motivated, okay.
Hi, Jeff. Thank you for the really nice talk. My name is Tyler. You had an example where the caching policy was learned, which was quite interesting, and it brings up the question of whether traditional computer science data structure and algorithms can be essentially learned. So like if we go back to the first class of computer science, we have like sorting algorithms and B trees and stuff like that, which is commonly used in systems. And maybe like for QSort, you have to pick the pivot really well for it to work. So wondering if you have any thoughts on how to improve that.
Yeah, I absolutely believe they can. Tim's talk later, I think, will touch on this. So in particular, he'll focus on some interesting computer science data structures like B trees and compare that with learned versions of B trees that are much better. And I think the key observation is with learning, you can actually observe the distribution of data your program is dealing with, as opposed to trying to make algorithms and data structures that are general purpose and have to deal with any adversarially bad sort of distribution of data. And you can take advantage of knowing the distribution in order to do all kinds of interesting things. And like cache replacement is a good example. Like LRU is just a heuristic that seems to work well for an awful lot of uses of caches, but it's not the perfect thing for any particular cache because often LRU doesn't work well for your workload.
Okay, I think we'll also touch on that at the panel, so do come.
Yeah.
Next question.
Hi, I'm Corey. It was an honor to hear your talk, first of all. But you mentioned a number of techniques for improving inference, but notably you didn't mention quantization. So I was just wondering if there was like something we could infer.
No, quantization is super important. I was making the slides last night and I already had 100. I did not throw in the 101st quantization slide so that we have time for questions.
Fair enough. Thank you so much.
All right, yeah. And I think lower and lower quantization is now becoming more possible. Like when we rolled out TPU v1, we weren't sure if we could quantize to 8-bit integers. Now people are like looking at 4-bit for production and 2-bit or 1-bit kind of quantization. Very important. Okay, thank you all.